For 6 episodes now, we have been circling a single question. Given the symbols seen so far, what is the probability of the next one? Solomonoff answered it in principle, the Bayesian frame unified it, and counting and context trees made it practical. Neural language models, the systems behind every chatbot you have ever used, are answering that very same question. The prompt you type is the history. The reply is one predicted symbol after another. Nothing about the target has changed. What changes is how they represent the answer.
But we already have counting and we already have context tree weighting. If those work, what is left for a neural network to do?
A fair challenge. Think about how a counting model stores what it knows. It keeps a table. For every context it has seen, a little tally of what came next. That table is the model. A neural model throws the table away. Instead, it holds a large bundle of adjustable numbers, its parameters, and it computes the probability of the next symbol by pushing the history through them. Learning means tuning those numbers until the computed probabilities match real text. That one move, from a stored table to a learned function, is what buys everything that follows. Nothing else about the problem moves. This single substitution does all the work. And notice the yardstick has not moved either. We still score a predictor by log loss, the number of bits it spends being surprised, exactly the measure from episode 1. Training a neural model minimizes the average bits it assigns to real text. A better predictor is still a better compressor. So the game is unchanged. Only the player is new, and the first thing this new player brings is a smarter way to represent a symbol. Here is something counting can never do. To a counting model, every distinct symbol is an island. The word cat and the word dog are just 2 different entries in the table, no closer to each other than the word cat is to the word the. So everything the model learns about dogs teaches it precisely nothing about cats. Every word has to be learned from its own occurrences alone, and the rare words are starved for data. A table with millions of contexts ends up memorizing far more than it generalizes.
So how does a network avoid treating every word as a separate island?
By giving each word a position and a space. Instead of an atomic label, every symbol becomes a dense vector of numbers, an embedding. And the network learns where to place it. Words that behave alike end up near each other, so cat drifts close to dog and Monday close to Tuesday. Now a sentence about dogs nudges that whole neighborhood, and cats quietly benefit. This is shared statistical strength. And it is exactly what atomic counting threw away. Bengio and his colleagues built the first model like this in 2003. Take the last few words, look up their embeddings, blend them through a network, and read off a distribution over the next word. Even a word the model has barely seen inherits some sense from its neighbors, and the starvation problem eases. But look at what has not changed. The model still only sees a fixed window of the most recent words. Widen that window and the network grows. The distant past still falls off the edge. To remember arbitrarily far back, we are going to need a different idea about memory itself. The different idea is to carry a running summary. A recurrent network keeps a single state vector, a fixed bundle of numbers that it updates one symbol at a time. Watch it work. Read a symbol, fold it into the state, move on. Read the next symbol, fold it in, move on. At every step, that state is meant to hold a compressed summary of the entire history so far, not just a fixed window. In principle, the memory is unbounded. Nothing about the length of the past is baked into the shape of the model. That was a real step beyond the fixed window.
In principle, that phrasing makes me suspicious. Does it actually hold on to the distant past?
Your suspicion is well placed. Everything the network knows about the history has to squeeze through that one fixed vector, and that is a narrow pipe. As the sequence runs on, the influence of the earliest symbols fades away, a difficulty the field named the vanishing gradient. Gated designs, the long short-term memory chief among them, added little valves that decide what to keep and what to forget, and they stretched the reach further. But even at their best, these models held on to something like tens of symbols, not thousands. And because each step waits for the one before it, you cannot spread the work out. The computation is stubbornly sequential. A summary that leaks, computed in a line you cannot parallelize. For a good few years, these gated recurrent models were simply the best we had for language. Then the next architecture went after both problems at once. The transformer, from 2017, throws out recurrence entirely. There is no state passed along a chain. Instead, every position in the sequence can look directly at every earlier position in a single step. Where the recurrent network reached the distant passed through a long fading chain, the transformer reaches it in one hop, from the very first layer. No summary to leak through. And because the positions are handled together rather than one after another, the work spreads across a machine beautifully. The recurrent bottleneck on speed is gone too, which is what lets these models train on truly enormous amounts of text.
Looking at every earlier position sounds expensive, and how does it decide which of them actually matter?
Both good instincts. The mechanism is called attention, and it runs on learned similarity. For each position, the model asks of every earlier position, how relevant are you to me right now? And it blends them together weighted by those answers. It is a soft, content-based lookup. Find the earlier words that match what I need and pull them forward. You are right that it is costly. Comparing every position against every other makes the work grow with the square of the sequence length. But it is worth it, and here is the punchline of the last decade. Take this one architecture, pour in more parameters, more text, and more computation all together, and the predictions keep improving along a smooth curve. Push that far enough, and you arrive at the large language models. We open the whole series with back in episode 0. And the strangest part is what Scale handed over for free. Abilities no one trained indirectly. Learning a fresh task from a couple of examples in the prompt, following a plain instruction, working through a problem step by step. They simply emerged as the predictor grew better at prediction. So we have climbed from counting, to embeddings, to recurrence, to attention. Before we crown a winner, remember the lesson from episode 3. Every predictor carries a prior. An assumption about what kind of structure the data has, and the prior is where the intelligence really lives. Solomonov's prior favored short programs. Context tree weightings prior ranged over trees. An n-gram assumes that only a fixed depth of the past matters. A neural network does not escape this. Its prior is simply hidden inside its architecture and its training data.
That surprises me. People say the transformer barely assumes anything, that it just learns from the data. Where is the prior hiding?
It is hiding in the shape of the machine. The transformer quietly commits to a few beliefs about language. That a distant word can matter as much as a nearby one. That understanding is largely pattern matching across the context. That meaning flows from past to future. And that structure builds up in layers, from letters to phrases to whole arguments. Those commitments are gentle compared to a rigid counting table, which is exactly why the model is so flexible. Feed it enough text, and that flexibility wins. But flexibility has a price, and it is the price the rest of this series has been careful about. Context tree weighting came with a guarantee. A proven bound on how much worse than the best tree source it could ever do. A neural language model offers no such promise. It hands you a single confident guess with no honest sense of its own uncertainty. So when it is wrong without warning. Enormous capacity and no safety net. Every predictor is a bargain between what it can represent and what it can promise. In the finale, we set counting, context trees, and neural models side by side, and decide which bargain to make and when.